Welcome. Today we're diving into one of the most fundamental concepts in computer science, queues and data structures. Queues are everywhere, from managing print jobs to handling tasks in operating systems. They're simple yet incredibly powerful. In this video we'll explore what queues are, how they work, and why they're so essential in programming. Whether you're a beginner or brushing up on your knowledge, understanding queues will help you write more efficient and organized code. Let's start by defining what a queue is and why it's so important in the world of data structures. Queue is a linear data structure that follows the first in first out or FIFO principle. Imagine a line at a ticket counter. The first person to get in line is the first to be served. Similarly, in a queue, the first element added is the first one to be removed. This simple rule makes queues perfect for situations where order matters. Queues are used in various applications, such as scheduling processes, managing resources, and even in everyday scenarios like waiting in line. Let's look at how this FIFO behavior shapes the way queues operate. Queues support a few basic operations that make them so useful. The two primary operations are enqueue and dequeue. Enqueue means adding an element to the end of the queue, while dequeue means removing the element from the front. There are also operations to check if the queue is empty or full depending on the implementation. These simple actions allow queues to manage data efficiently and maintain order. Understanding these operations is key to using queues effectively in your program. Let's take a closer look at the enqueue operation. When you enqueue, you add a new element to the rear or end of the queue. Think of it as someone joining the back of a line. This operation ensures that new data waits its turn behind the existing elements. In most programming languages, this is a straightforward process, but it's crucial for maintaining the FIFO order. Enqueuing is the first step in getting data into the queue for processing. Now let's talk about the dequeue operation. Dequeue removes the element at the front of the queue, just like the first person in line gets served and leaves. This operation is essential for processing data in the order it arrived. If the queue is empty, dequeue usually returns an error or a special value depending on the implementation. Dequeuing keeps the queue moving and ensures that no data is skipped. Besides enqueue and dequeue, queues often support a peek operation. Peek lets you look at the element at the front of the queue without removing it. This is useful when you need to know what's next to be processed, but you're not ready to remove it yet. Peek helps in scenarios where you want to check the upcoming task or data without altering the queue's state. Queues also provide methods to check if they are empty or full. The isEmpty operation returns true if there are no elements in the queue, while isFull is relevant for queues with a fixed size like array-based implementations. These checks are important for preventing errors, such as trying to dequeue from an empty queue or enqueue into a full one. They help keep your program safe and efficient. There are several ways to implement a queue in programming. The two most common methods are using arrays and linked lists. Each approach has its own advantages and trade-offs. Array-based queues are simple and fast but have a fixed size, while linked list queues can grow dynamically but may use more memory. Choosing the right implementation depends on your application's needs. Array-based queue uses a fixed size array to store elements. It keeps track of the front and rear positions to manage where elements are added and removed. This method is efficient for small, predictable workloads, but it can run into problems if the queue fills up. When the array is full, you can't add more elements unless you resize or use a circular queue. A linked list queue uses nodes connected together, allowing the queue to grow and shrink as needed. Each node contains data and a reference to the next node. This approach avoids the fixed size limitation of arrays and is ideal for situations where the number of elements can change frequently. However, it may use more memory due to the extra pointers. Circular queue is a special type of array-based queue where the last position is connected back to the first. This design allows you to reuse empty spaces at the front when elements are removed, making better use of memory. Circular queues are great for buffering data streams or managing resources in a loop. Priority queue is a variation where each element has a priority, and elements are served based on their priority rather than just their order. This is useful in scenarios like task scheduling, where some tasks need to be handled before others. Priority queues are often implemented using heaps for efficient access. Double-ended queue, or Deque, allows elements to be added or removed from both the front and the rear. This flexibility makes Deques useful for a variety of applications, such as undo operations in software or managing both ends of a data stream. Deques combine the features of stacks and queues. Queues are used in countless real-world applications. They manage print jobs in printers, handle requests in web servers, and organize tasks in operating systems. Queues are also essential in simulations, customer service systems, and even in traffic management. Their ability to maintain order and process data efficiently makes them a go-to solution in many fields. In operating systems, queues play a vital role in process scheduling. When multiple processes need CPU time, they're placed in a queue and served in order. This ensures fairness and efficient use of resources. Queues also manage input-output requests and help prevent bottlenecks by organizing tasks systematically. Networking systems use queues to manage data packets as they travel through routers and switches. Each packet waits its turn in a queue before being forwarded to its destination. This helps prevent data loss and ensures smooth communication between devices, especially during high-traffic periods. Customer service systems often use queues to manage incoming requests. Whether it's phone calls, emails, or chat messages, each request is placed in a queue and handled in order. This approach ensures that every customer is served fairly and efficiently, improving overall satisfaction. When you send multiple documents to a printer, they're placed in a print queue. The printer processes each job in the order it was received, ensuring that documents are printed correctly and efficiently. Print spooling is a classic example of queues in action. Simulation systems, such as those modeling traffic or customer flow, use queues to represent waiting lines. By simulating queues, these systems can predict bottlenecks, optimize resource allocation, and improve overall efficiency in real-world scenarios. Resource management systems use queues to allocate limited resources, such as CPU time, memory, or bandwidth. By organizing requests in a queue, these systems ensure that resources are distributed fairly and efficiently, preventing conflicts and maximizing performance. In algorithms like breadth-first search (BFS), queues are used to explore nodes level by level. By enqueuing each node's neighbors, BFS ensures that all nodes at the current depth are processed before moving deeper. This systematic approach is only possible because of the queue's FIFO nature. Task scheduling systems rely on queues to manage jobs waiting to be processed. Each job is added to the queue and executed in order, ensuring that no task is skipped or delayed unnecessarily. This approach is common in batch processing and background task management. Real-time systems, such as those in embedded devices or robotics, use queues to manage time-sensitive tasks. By processing tasks in the order they arrive, queues help maintain system stability and ensure timely responses to critical events. Multimedia streaming services use queues to buffer audio and video data. As data arrives, it's placed in a queue and played in order, ensuring smooth playback even if network speeds fluctuate. This buffering technique relies on the queue's ability to manage data flow efficiently. E-commerce platforms use queues to manage orders, payments, and inventory updates. By processing each transaction in order, queues help prevent errors and ensure that customers receive accurate information about their purchases and deliveries. Messaging systems, such as email servers or chat applications, use queues to handle incoming and outgoing messages. Each message waits its turn in the queue, ensuring that communication is orderly and reliable, even during peak usage times. Cloud computing platforms use queues to manage tasks across distributed systems. By organizing jobs in queues, cloud services can balance workloads, scale resources, and ensure that tasks are completed efficiently, even as demand fluctuates. Data processing pipelines use queues to manage the flow of data between different stages. Each stage processes data from the queue and passes the results to the next stage. This modular approach improves scalability and makes it easier to handle large volumes of data. Robotics systems use queues to manage commands and sensor data. By processing each command in order, robots can perform tasks reliably and respond to changes in their environment. Queues help ensure that no instruction is missed or executed out of sequence. In gaming, queues manage player actions, event triggers, and network messages. By organizing these elements in queues, games can provide smooth gameplay, handle multiple players, and synchronize events across different devices. Web servers use queues to manage incoming requests from users. Each request is placed in a queue and processed in order, ensuring that every user receives a timely response. This approach helps web servers handle high traffic and maintain reliability. Database systems use queues to manage transactions and queries. By processing each operation in order, queues help maintain data consistency and prevent conflicts, especially in environments with multiple users or applications accessing the database simultaneously. Event-driven systems use queues to manage events as they occur. Each event is placed in a queue and handled in order, allowing the system to respond predictably and efficiently to user actions, sensor inputs, or other triggers. Load balancing systems use queues to distribute tasks across multiple servers or resources. By organizing tasks in queues, these systems can prevent overload, improve performance, and ensure that resources are used efficiently. Manufacturing systems use queues to manage production lines and inventory. Each item moves through a series of queues as it's assembled, tested, and packaged. This organized approach helps streamline operations and reduce delays. Healthcare systems use queues to manage patient appointments, test results, and medication orders. By organizing these tasks in queues, healthcare providers can deliver timely care and ensure that no patient is overlooked. Transportation systems, such as airports and public transit, use queues to manage passengers, vehicles, and cargo. By organizing these elements in queues, transportation providers can improve efficiency, reduce wait times, and enhance safety. Financial systems use queues to process transactions, manage account updates, and handle customer requests. By processing each operation in order, queues help maintain accuracy and prevent errors in critical financial operations. Security systems use queues to manage access requests, alarms, and incident reports. By organizing these events in queues, security teams can respond quickly and ensure that every issue is addressed in a timely manner. Education technology platforms use queues to manage assignments, grading, and student queries. By processing each task in order, these systems help teachers and students stay organized and ensure that everyone receives the support they need. Social media platforms use queues to manage posts, notifications, and user interactions. By organizing these elements in queues, platforms can deliver content efficiently and provide a smooth user experience, even during peak activity times. Artificial intelligence systems use queues to manage tasks, data inputs, and model training jobs. By processing each task in order, AI systems can learn efficiently and deliver accurate results, even when handling large datasets. Research and analytics platforms use queues to manage data collection, processing, and reporting. By organizing these tasks in queues, researchers can ensure that data is handled systematically and results are delivered on time. Workflow automation systems use queues to manage tasks, approvals, and notifications. By processing each step in order, these systems help organizations streamline operations, reduce manual effort, and improve productivity. Wrap up, queues are a simple yet powerful data structure that play a crucial role in countless applications. From operating systems to customer service, queues help maintain order, improve efficiency, and ensure fairness. By understanding how queues work and where they're used, you can design better programs and systems. Remember, the key features of queues are their FIFO nature and their ability to manage data flow efficiently. Thanks for joining this journey into the world of queues and data structure.